Hello all Royal Rangers, my name is Commander Matthew Kenslow and I'm over here in the United States of America, and I've been a Royal Ranger for 20 years and year number 7 as a commander. Thank you so much for checking out this video. The purpose of this video is to go over a merit. In these videos I'm going to walk through every one of the requirements. Now it's important to note that while watching these videos it will not give you the merit. You have to show to your commander that you have watched and learned from these videos. What I recommend you doing is taking down notes for each requirement and then show them to your commander for approval. Some of the purposes of Royal Rangers is to build knowledge, wisdom, skills, and leadership attributes while learning about God's Word and conserving His resources practically. And most importantly, to have fun doing it. So I'm Commander Matthew Kenslow from the United States of America, and be blessed. Hi everybody, welcome to the chemistry merit. It's an incredible merit, and you're going to learn a survey of the different types of chemistry, as well as some of the history of chemistry and basic knowledge of chemistry. Just as a quick background of who I am is that I earned an associate in science degree in chemistry from Orange Coast College back in 2018. In the summer of 2020, I was a scientist for my undergraduate research for Vanguard University as I pursue a bachelor's in biochemistry. As of the filming of this, I have one more semester before a bachelor's degree. I was interning as a biogeochemist at SCCWRP, analyzing muscle tissue, SPE cleanup, and such. So here I am in front of the loading stage of the protocol, and I had to do this many times, along with other things such as sonicate, turbovap, centrifuge, eluting, and not necessarily in that order. So it was a fun and interesting summer. I am blessed to say that I got like the best quality research out of everybody. There were 3 awards and I was one of them, so I'm very thankful for that. Anyway, this merit can be completed by earning at least a grade of B for 2 semesters of high school chemistry, or by completing the following requirements. So let's begin with requirement 1. Define the science of chemistry, explain what chemists do, and how their contributions have improved our standard of living. So again, this is just going to be a survey of chemistry. The science of chemistry is the study of atoms and molecules and how they interact, react, and combine. Chemists study the way atoms interact to form molecules and how molecules interact to form new molecules. By understanding the rules that govern those interactions, chemists can take simple materials and make vast numbers of new materials that either substitute for natural materials or form materials that have never before existed, and that will get into inorganic and synthetic chemistry. Chemists can make things better, safer, cheaper, and more available by understanding how matter undergoes changes to produce materials that enrich our lives. First of all, matter is anything that has mass or volume. So anything that has weight and takes up space. Many of these materials are the result of works by chemists. Chemistry improves our foods and develops modern medicine. Even the space program is dependent upon chemistry. Rubber, nylon, plastic, gasoline, food additives and preservatives, pharmaceuticals, and many other substances used by everyone every day are the result of the study of chemistry. Requirement 2. Complete the following. So this is something that you're going to do at home. List at least 5 chemical products that you use at your home. Examine the labels of the chemicals. List what the manufacturer puts on the container, including warnings, harmful effects, and medical aid. Contact your community solid waste management system for information listing the proper disposal of household chemicals. When I was taking lab over at Vanguard University and SCCWRP in the summer of 2020, we had to be very careful on what could go down the drain and what goes inside waste containers, because some waste cannot go down the drain. Okay, requirement 3. Define the branches of chemistry listed below. Explain each branch's area of study and contributions. Chemistry is a vast field, and there are different branches that you could pursue. You could take general chemistry, organic chemistry, physical chemistry, biochemistry, which is my major, and so on. And so here I'm going to list some different branches. One of them is inorganic. Inorganic chemistry is the study of chemistry of non-living processes. Inorganic chemistry can also be considered the chemistry of any compounds that, with few exceptions, do not contain carbon. Over 100 elements are known, and the compounds they can form, with the exception of the carbon-containing organic compounds, are almost limitless. Many thousands of inorganic chemicals are known, with more being discovered or synthesized each day. Synthesize means to put together or build. Through the study of inorganic chemistry, advances in alternate uses of metals have been made. Okay, organic chemistry. Organic chemistry is the study of carbon compounds and their chemistry. Theoretical organic chemists study the geometry of these compounds, while others study the rates of other physical parameters of those reactions, and that's typically in the field of kinetics, physical chemistry. Applied organic chemists study ways in which to synthesize new compounds that may be important in things like medicine and manufacturing. Others research new and important uses for organic chemicals that are not made in laboratories but are found in nature. Because organic chemistry is the study of carbon, all living matter has carbons, us humans, animals, plants. Here's something that I've done in the lab, well, kind of bit partly. In my organic chemistry 2 lab, we took benzaldehyde and added a few things to make benzoin crystals, and then took that the next week to make benzo crystals, and that was early 2020. Unfortunately, I had the flu in late January 2020, so one of my friends did the first step, but I did the rest. I took benzoin crystals and made benzyl. And here is something that I have on YouTube if you're interested to see organic chemistry in action. This is the apparatus that I assembled one of those weeks, and it's pretty neat. We were synthesizing crystals, so that's on YouTube if you're interested. And then the final week, we took the benzo crystals and added dibenzyl ketone and some inorganic agents to make tetraphenylcyclopentadienone. And yes, that's one word, and I was actually pretty excited. I mean, I synthesized it, and I also memorized the structure as well, and it's pretty systematic. These long words shouldn't be intimidating. You just break them down, and it's easy to take almost anything you never heard of and be able to infer what the structure is. For example, a ketone has a carbonyl group, and the carbonyl carbon is attached to 2 R groups. So what's carbonyl? Carbonyl is a C double bonded to an O. This point right here is a C. This is the line angle structure. And then, since this carbonyl carbon, as we call it, is bonded to 2 alkyl groups, or 2 carbons, basically, then this is a ketone. And then the dibenzyl means that you have 2 benzene rings. And I do want to clarify why it's called tetraphenylcyclopentadienone. As I was saying earlier, a lot of things in science is very systematic. And if you just break it down, tetra means 4, and it's right in front of phenyl. What's phenyl? It's basically benzene without a hydrogen, and that means it adds as a substituent. And you have those 4 rings, and as a substituent, they're called phenols. So tetraphenyl, so 4 phenyl groups, and they're attached to the pentagon, as you see right here. Well, a pentagon has 5 points, right? Thereby standing for 5 carbons. And if it was just in a linear line angle structure, that would be pentane. But because it's a circle, it would be called cyclopentane. But first of all, it's not called pentane, it would be called pentene. And it would be called that because whenever you have a C double bonded to another C, so carbon double bond carbon, then that would be an ene. You would have to add ene in there. And since there's 2 of them, you could see 2 double bonds inside the pentagon or the ring structure. It would be called a diene because di means 2, so you have 2 CC double bonds. And they are inside the cyclopenta part of the molecule, so it would be called cyclopentadiene. Because you have the C double bond to O right up there, then it's a ketone and you have to add the suffix -one, so tetraphenylcyclopentadienone. And as I was telling everybody and drawing the structure, even in my non-science classes, I was likening the structure so much to a human jumping for joy. So I'm thinking that tetraphenylcyclopentadienone's got to be somebody's logo one of these days. Maybe a science company, and they'll use that. So just a little preview to organic chemistry. Here's a picture of taking the benzyl crystals and forming tetraphenylcyclopentadienone crystals right here. So this was before and this was after. So it's there are dark crystals here. We also do or have done steam distillation. This was the semester previous, and so organic chemists could extract things such as essential oils. So in this case I was extracting the essential oils from the rosemary plant that I picked outside the lab at Vanguard University, and with steam distillation I extracted the essential oils. I heated it up, and then the evaporated gases went up here and then condensed back into a liquid. It dripped down into this flask right here, and that's where we collected the distillate. And then we rotovapped it, and what was left over was the essential oils. And again, mine was rosemary. Okay, so notable discoveries of organic chemistry include fossil fuels. Organic chemists discovered how to take crude petroleum from the ground and make all the different types of fuels used today, known as catalytic cracking, followed by fractional distillation. Plastics. Organic chemists, again working with petroleum compounds, discovered all the types of plastic polymers known today, such as vinyl, nylon, PVC, which is polyvinyl chloride, polyethylene, polypropylene, plastic foam, etc. In fact, when you were younger, if you were in Rangers, you probably took rope craft and learned about different types of synthetic rope. Polyethylene, polypropylene, nylon are a couple of examples of synthetic rope. Adhesives. Organic chemists discover many of the compound adhesives, such as glues and superglue. And drugs and medicines. These are used in most pharmaceuticals. These include antibiotics, narcotics, and vitamins. Here I have a picture of something that I put together when trying to understand half-chair conformations. So organic chemists study different conformations or shapes and structures of molecules. So when you take organic chemistry, you'll probably learn about Newman projections and chair conformations and such, because we're interested a lot in the shape of molecules, what's more favorable and unfavorable energetically. Okay, physical chemistry. Physical chemistry is the study of how chemical compounds do what they do, the rules of motion and energy as they apply to chemistry, or the behavior of molecules. While organic and inorganic chemists study what certain molecules will do in certain circumstances, physical chemists study the how and why of those same behaviors. Physical chemists, just like physicists, will use mathematics more than words to describe what they study. Physical chemistry is divided into various disciplines depending on the aspect of the physics of the chemical reactions they are interested in. So before you take physical chemistry, of course, take the general chemistry for sure, but also physics, because you need physics a lot in order to understand physical chemistry. Here's just an example of a physical chemistry problem deriving a specific formula that I did on the whiteboard, trying to make sense of what I'm reading in my textbook. And I will not lie, physical chemistry is very intense. I do like math, but as my physical chemistry instructor told me in his office, he said, this is kind of a bit like physics and calculus on steroids, and he wasn't lying. You need to know the basics, but you know, you really have to pay close attention and take time to study these things. You'll be doing a lot of calculations, like finding delta G, or the Gibbs free energy values for spontaneity. You're going to calculate a lot of other values, the van der Waals equation of real gases versus ideal gases and such. And also get used to using a spreadsheet is my advice as well, like Excel, for example. And so these are only 3 of the many, many pages that I filled while taking those classes, because there's 3 main classes of physical chemistry, and we all have to take thermodynamics, but we had a choice between kinetics and quantum mechanics, and you just need to take one or the other, especially if you're a biochemistry major like me. Kinetics is the one I chose because that's more the chemistry route, and quantum mechanics is more the physics route, and I'm more chemistry minded, so I chose kinetics, but that was also math intensive as well. And also, one huge advice that I would give to anyone in a heartbeat is also take a statistics class before tackling physical chemistry. So I added this right here, this graphic right here, and this is just an example of an energy reaction graph when you learn about thermodynamics, kinetics, using a catalyst and such, finding intermediates and all that, and determining what's favorable or unfavorable, if it's exergonic or endergonic or exothermic and endothermic and such. And you'll learn all that in a basic thermodynamics class. So thermodynamics is concerned with the energetics of chemical reactions, what kind of reactions can occur, what drives those reactions, and in what conditions they can occur, how far the reactions can go, and how much one can expect to get from a reaction. Kinetics studies the rates of the reactions and their probabilities. Quantum mechanics study the rules governing the behavior of the atoms in various chemical reactions. In turn, these 3 divisions are subdivided into various applied disciplines such as electrochemistry, colloid chemistry, photochemistry, and statistical and chemical thermodynamics. And we'll be briefly talking about those later on in this merit. Contributions include the development of a supersonic molecular beam technique for the study of clusters, ions, and molecules. Synthetic chemistry. Synthetic chemistry is concerned with using chemistry to make a desired compound, rather than the study of the rules of chemistry. Synthetic chemists can be inorganic chemists or organic chemists, but are most often organic chemists. These specialized organic chemists use a variety of known chemical reactions as tools to make desired compounds from available compounds. Typically, a synthetic chemist will first plan out a protocol to follow when making a needed chemical from materials at hand. So a protocol is like a step-by-step list to do. I've followed several of them in school and at SERP, which is the undergraduate research program that I was in. He will then follow this protocol to get what he needs. Usually, some steps may not work exactly as planned, so alternate plans will be made and used until the project succeeds. Synthetic chemistry contributes greatly to the development and production of new and advanced medical drugs. Analytical chemistry. Analytical chemistry is a very practical form of chemical study. It is usually divided into 2 types, quantitative and qualitative. I just completed a semester just prior to filming this, and this is basically the things that you learn in general chemistry, just a bit more advanced, as well as statistics. So don't do what I did and go through all these classes without taking a statistics course, because for me, I never needed statistics in order to get my AS degree and my future bachelor's degree. However, it would be very advantageous for you to take statistics, so I sort of exhort or urge you to make time to take a statistics class because it will really help you. Quantitative chemistry is used to determine how much of a given substance is present. Qualitative chemistry is used to identify an unknown compound. Environmental chemists use qualitative chemistry to determine what kinds of nutrients or pollutants are in the environment, and then use quantitative chemistry to determine how much of these nutrients or pollutants are found in the environment. Water chemists use quantitative and qualitative chemistry in similar ways, but examine drinking water and or wastewater. So basically, quantitative chemistry is where you could take a mathematical value and quantify things and apply them to things, such as mass, volume, and length. And qualitative chemistry, you could think about it where you can't put a mathematical value to it or quantify it, such as odor, taste, and color. Okay, biochemistry, my major, and I just took the first class this past semester concurrently with analytical chemistry. Biochemistry is the study of the chemistry of life. Inside all living things, many chemical reactions continually occur. All of the processes of life are biochemical in nature. Due to the extreme complexity of this living chemistry, there are several subdisciplines within the field of biochemistry. Some biochemists study the processes of the making and recycling of the various biomolecules called metabolism and catabolism respectively. Well, metabolism is basically all the chemical reactions that are inside of you. Catabolism is when things like big molecules are broken down in the body or out in nature in other forms of life like animals, plants, and anabolism is the building of molecules from smaller molecules. Biochemists who study the thermodynamics or kinetics of biochemical processes are called physical biochemists. I would suggest to you that before taking biochemistry, or maybe concurrently, consider taking physical chemistry kinetics, because you're going to learn about, Michaelis-Menten kinetics, for example, that's going to be seen in biochemistry and such. So there's a lot of rates of reactions, first order, for example, in biochemistry, on top of learning about the four basic biomolecules: carbohydrates, lipids, which are your fats, nucleic acids, and proteins. And it's typically when you learn about proteins, specifically enzymes, when you learn or relearn about kinetics. Protein biochemists study the chemistry of proteins in living cells. So proteins could include enzymes, like I was talking about a few seconds ago. These proteins can either be part of the structure of living tissue, such as muscle proteins, such as channel proteins in the plasma membrane, or they can be the chemical catalysts called enzymes. A catalyst is something that helps speed up the reaction without itself undergoing change, and you'll learn probably more about that while taking chemistry and biology. Here's an example of a protein structure. There are four different structures. The primary structure is the amino acid sequence. So these are amino acids such as glycine and tryptophan, for example, or leucine and such. And then the secondary structure analyzes how they react with each other. And that depends on the functional groups that are coming off of these individual amino acids. Do they create some interactions, such as dipole interactions or hydrogen bonds, for example? And due to the sequence, they could coil in these alpha helices, or they could fold into these beta pleated sheets, for example. And then there's the tertiary and quaternary structure as well. Carbohydrate chemists study the chemistry of sugars and starches. So that's what carbohydrates are. You have basic monosaccharides such as glucose, galactose, and fructose. If you have two glucose bonded together, that creates maltose. If you have glucose and galactose bonded together, you get lactose. And when you have glucose and fructose bonded together, then that's called sucrose, which is table sugar. When two sugar molecules bond together, it's called a disaccharide. Di means two. Individually, it's a monosaccharide. Mono means one. And these could form long chains called polysaccharides as well. That's where you get glycogen and chitin, for example. Nucleic acid chemists study the chemistry of DNA and RNA, the information storage and expression molecules of life. So here's an example of DNA, and here's one of RNA. So you can see that DNA is double-stranded, RNA is single-stranded. DNA has thymine, but RNA has uracil. And we'll look into DNA a little bit later. So I just want to just say a little summary of what I found personally, is that biologists and biology typically looks at the structures, at the overall structure, Here you have the phospholipid bilayer and the channel proteins, as well as lipids or the fats, such as cholesterol and glycolipids, which are both carbohydrates and fats, as well as glycoproteins, which are both carbohydrates and proteins. But biochemists study and look at the individual atoms. So here, let's take one phospholipid right here. So here you see like a circle and two lines. This is it right here too. Well, this is basically a quick way to represent it, but in reality, these are molecules inside of here. You have two fatty acid tails, one that's saturated, one that's unsaturated. That's why there's a kink there. And there's a kink there because you have a double bond that you could see here. I'll get to this structure in a few seconds, but these are bonded to what was glycerol right here, and then you have a phosphate group creating a charge here, making this head polar. But since this is a hydrocarbon chain, this is unpolar, and that's what gives it the properties. And you'll probably learn more about the phospholipid bilayer when you take biology. But my point here is that biochemists don't typically always look at these simple, pleasing to the eye, basic shapes, structures. They actually look at the atoms inside each one of these, as well as the structure of the bilayer, these proteins right here. So whenever you see like helices like these, then it's typically denoting proteins and all that. As well as looking at the individual atoms and molecules bonded together. So that's what I got after all these years, is that biology looks more like this and the big picture, and then biochemistry gets all the way down to the nitty-gritty. Okay, organometallic. Organometallic chemistry studies organic or carbon compounds that bind metal atoms. That's why it's called metallic, for metal. And since it's organic or compound carbons, that's why it has organo in there. So this is basically a hybrid of two words, or basically like what you see all over science are small root words, prefixes, suffixes, just put together. This is an important field in biochemistry, since many vital biomolecules will bind metals for them to function. The most noticeable of these compounds is the molecule that makes blood red. Many enzymes are organometallic compounds binding iron, chromium, magnesium, and other metal atoms. Organometallic chemists study the structure and behavior of these compounds of life, as well as many other carbon-containing molecules that bind metals. These non-living molecules are all around us. Many dyes are this type of molecule. So I just want to give an example. This is kind of what I was just reading about. This is hemoglobin. So in our blood, we have all these red blood cells known as erythrocytes, white blood cells known as leukocytes, platelets known as thrombocytes, and all the proteins to help bind them together when you get a cut and all that. But red blood cells contain hemoglobin. Inside hemoglobins, you have these four globin molecules, 2 beta and 2 alpha, bonded together. And inside each chain is another molecule called heme, or a heme group. Inside each heme is an iron metal, and that is what causes oxygen to bind to it. If you are familiar with anatomy and the circulatory system, then you would know that blood rushes to the heart, which is pumped to the lungs, and once it gets into the lungs, it travels in these blood vessels here to receive oxygen. So when we breathe, air, well, oxygen especially, gets in our lungs and starts to fill our lungs. Oxygen is now inside these alveoli sacs right here, these grape-like structures, and the blood picks up the oxygen, and that's when it changes from blue to red, and then it goes back to the heart and then pumped through the aorta to the rest of the body, and then it gives off that oxygen to the cells of the body, and that oxygen helps out a lot with especially metabolism and such. And well, you'll probably learn more about cellular respiration later on, and aerobic respiration, but that's the basics. So it's because of this iron inside the heme, inside the globin molecules, to hemoglobin that causes oxygen to bind to it, and that's basically why blood is red. In our muscles, you also have myoglobin, which is what makes muscle red as well. And so this is an example of organometallic chemistry, one of the things that they would study. Okay, requirement 4. Explain how and why organic and inorganic chemistry separated into two separate fields. Remember what organic chemistry is. It's basically the study of carbon. So this one element right here, element number 6, is basically what makes up an entire field of chemistry. Early 19th century chemists began to understand that matter is made up of elements or atoms, and that those elements could combine to form mixtures called compounds. Compounds were discovered to possess two or more elements in fixed proportions. By any chance, do you know the difference between a molecule and a compound? Well, all compounds are molecules, but not all molecules are compounds. Basically, a molecule is whenever you have two or more atoms bonded together. But if they are different atoms, then they're known as a compound. But something like oxygen or nitrogen or hydrogen, so I'm talking about O2, N2, H2, for example, then those are just molecules because it's made of one type of atom. Something like CO2, CO, H2O, for example, those are examples of compounds. Chemists began to notice that the compounds found in living matter almost always had the element carbon in them. The chemistry of carbon is more complex than many of the other elements. It was soon noticeable that the study of the chemistry of living compounds was essentially the study of carbon compounds. The exceptions to this are few: carbon monoxide, carbon dioxide, carbonates, cyanides, cyanates, thiocyanates, or cyanates containing sulfur, that's what the thio prefix denotes, or certain carbides. Two branches of chemistry thus came into being, one being the study of carbon and compounds from living things, and the other being the study of compounds of non-living things. The first was called organic chemistry, since it was the chemistry of living organisms. If you get it, things like a person, a plant, an animal, they're called organisms. And since carbon is found in living organisms, then it's called organic chemistry, or basically that's why it's called organic chemistry, because it's kind of studying living organisms, organic and organisms, okay. And the other was called inorganic chemistry, which is not organic chemistry. This division was strengthened because the rules of each seemed to be quite different from the other, and early chemists could not convert compounds that were inorganic into organic compounds, or vice versa. Okay, requirement 5. Describe the important scientific contribution Friedrich Wohler made to organic chemistry. So here's a picture of him. And what he did is that he synthesized urea. Now, urea is an organic compound, and prior to Wohler, people thought that you cannot synthesize organic compounds, and that organic compounds were synthesized naturally inside living organisms. But like I just said, he went on to synthesize urea, which is an organic compound. Since the early chemists seemed unable to convert inorganic compounds into organic compounds, they speculated that a vital or living force was required to make the organic compounds. And this kind of bit reminds me of the spontaneous generation that people believed hundreds of years ago, something that you probably will learn in microbiology. In 1928, German chemist Friedrich Wohler disproved this and succeeded in making the first artificial organic compound. He heated an inorganic compound, ammonium cyanate, and formed the compound urea, which is a compound found in urine. Now this triangle here denotes heat, so whenever you see a chemical equation, you see the arrow here, well, whenever you see a triangle, that means heat was added. By this time, however, the divisions between inorganic and organic chemistry had largely formed and persist today. Carbon does have a vast repertoire of chemical transformations that it can undergo and can form almost limitless numbers of compounds. Since virtually all chemistry in living organisms involve carbon, organic chemistry is really the chemistry of carbon. Today, many chemists make carbon compounds that are unlike any compounds ever formed in living things. But by virtue of the fact that they are working with carbon compounds, these chemists are still called organic chemists. Okay, requirement 6. Describe the difference between theoretical and technological inorganic chemistry. Theoretical inorganic chemistry is the study of the general laws and principles that underlie all chemical processes. It is the objective of this study to understand the laws so well that new compounds and chemical processes can be invented by applying this understanding. Once the theories behind the behavior of chemical compounds are understood, those theories can be used to solve practical problems. Technological inorganic chemistry is the applied science of chemistry to achieve defined goals or products. Okay, requirement 7. Describe the development of the what by Russian chemist Dmitri Mendeleyev. Explain how this theoretical concept was useful. So what do you think goes in the blank? Had you ever heard of Mendeleyev before? Here's a picture of him. What do you think this is a picture of right here? Well, this right here is the original periodic table that Mendeleev came up with or helped develop. So we're going to describe the development of the periodic table. So to honor his legacy, element 101 is called Mendelevium, named after Mendeleev. First, let's talk about the Dobereiner triads. Johann Wolfgang Dobereiner determined that if you order the elements based on atomic mass, there are certain properties that arise. If you list lithium, sodium, and potassium, the average of their atomic mass is the mass of the middle one. So you take the average, that means you take the sum of the three, and you divide by 3. Here they just took the first and the third and then divided by 2, but still it's approximately the same as the middle one. Same thing with calcium, strontium, and barium, and with phosphorus, arsenic, and antimony, and onward. The only thing is, it only worked for certain elements, or certain groups of 3, known as triads, but not all of them. But that was some observation, and of course these do exhibit similar properties. These were later known as the alkali, or part of the alkali metals, the alkaline, and such. But later on, you have John Newlands. Now, he came up with the Newlands octave, that if you order the elements based on the atomic mass, or the known elements of the time based on atomic mass, then similar properties will recur periodically. Kind of a bit like octaves in music. So the prefix in octaves refers to 8, like octopus, October, octagon, octillion, for example, and it essentially states that every 8th element will have a similar property. So at the time, there were just under 60 elements known. It does not work past calcium, and if you're wondering where helium, neon, argon, etc. are, it doesn't include the noble gases because they weren't discovered yet. Some positions have 2 elements of differing properties as well. Now on to Dmitri Mendeleyev and Julius Lothar Meyer. Now both of them came from different countries, Russia and Germany respectively, and they sort of proposed the periodic table around the same exact time. The only thing is that Mendeleev, and by the way, this is an alternate spelling of the same name, just to say, but Mendeleev had more credence in his periodic table, and it was also published a year earlier than Meyer. However, Mendeleev had to revise his periodic table, and this is the one that was published in 1871. And you could see here the elements like hydrogen and the atomic mass of 1, lithium, the atomic mass of 7. All the numbers here are the atomic masses, like oxygen is 16, for example. But let me put this in a format where it's more visually appealing, as well as a review of the Dobereiner triads. So here's Mendeleev's periodic table right here. Everything in blue were unknown. Here are the noble inert gases right here, and these ones in blue weren't discovered yet. And you could see there's still a correlation between the Dobereiner triads within the same column, as you see here. Now I especially blocked out these 3 elements right here because I want to show you what had Mendeleev's periodic table accepted in the scientific community. Not everybody agreed to use Mendeleev's periodic table at first, but Mendeleev was very intelligent that he made some predictions of what could go inside these spaces. Because you could see here, there's just some dashes right here. Now I want to highlight this element right here in orange, and this was known as ecosilicon as a placeholder name. And here are Mendeleyev's predictions for ecosilicon. Recall that this element right here was not discovered yet, but Mendeleev predicted the atomic mass, the density, that it would have a high melting point, grayish in color, and so on and so forth, as you can see here. So he went ahead and calculated and made predictions, and later germanium was discovered. It was discovered in 1886. Now let's go over the properties, the actual properties of germanium, and compare them to Mendeleev's prediction. The actual atomic mass was 72.61. The density is 5.35. It has a high melting point. It is grayish in color, as you can see here. And the oxide density is 4.7, and so on. And you could see that it's almost exactly what Mendeleev predicted, and that helps solidify the accuracy of Mendeleev's periodic table, and that's what had it accepted in the scientific community all around the world. Unfortunately, Mendeleev never earned a Nobel Prize. However, he did have that element named after him, element 101. Now let's talk about gallium. Mendeleev had a prediction about gallium before it was discovered, and here's his predictions next to the actual properties of gallium. Gallium's neat because it could melt in your hand upon contact, and that wasn't discovered until 1875. Now let's talk about Henry Moseley. English physicist Moseley deduced that each type of atom contains the same number of protons. Oxygen will always have 8 protons. Different elements can have different masses. Some have isotopes, for example, and we'll probably get to that later. But therefore, the atomic number is more fundamental than the atomic mass. Recall that previously they would order the elements based on atomic mass, but Moseley started to order them based on the atomic number, and the atomic number is how many protons there are in that atom. For example, oxygen has 8, hydrogen has 1, rutherfordium, not that it's been synthesized yet, has 104. And now here is the current periodic table as it is as of the filming of this, and there's 118 elements known, and this is kind of a bit neat. It's color-coded based on the discovery. So, for example, everything in blue were discovered between 1735 and 1843 and such. In fact, I remember it was right after my first chemistry class at Orange Coast College in 2015, and I looked on Facebook, and one of the #1 trending things was that the last 4 elements were synthesized. Well, it wasn't the last 4 elements, it was 113, ununtrium, union pentium, union septium, and union octium. That's how I and everybody else referred to them prior to this time. And then in the next year, it was trending again on Facebook that there's names given to them now. So you have nihonium, moscovium, tennessine, and agnesium. And what's interesting is that later that year, in the fall of 2016, I was taking the next chemistry class along with the lab, and the TA just happened to know a person who knows the person that number 118 agnesium was named after. It was interesting, but he kind of knows of a person who knows of a person of the person who was named after this element. But anyway, the periodic table kind of been the source of memory challenges and such, and I accepted that challenge, and on July 21st, 2014, I had all 118 elements memorized, well, the current ones, to an extent that I corrected the periodic table in my biology class. The teacher put up a slide of a periodic table that had something wrong in it, but I just couldn't help to correct it. But anyway, just to say, no chemist on the planet really needs to have this memorized or whatnot, and I only memorized the names, not all of their atomic masses or or atomic numbers or whatnot, just the names and the order. But you don't have to memorize it for the merit. Okay, requirement 8 is define any two of the following areas of physical chemistry. Now I'm going to go through all of them, and it's up to your commander what he would want. Maybe he would want you to choose two of the ones that I'm going to go over and maybe do an extra study, or maybe have it written down in your notes or whatnot. But anyway, just keep it up with the notes and show it to your commander. He might just check you off on it. But anyway, define any two of the following areas of physical chemistry. Now remember, physical chemistry is basically chemistry and physics with thermodynamics and kinetics and quantum mechanics and such. So let's start with electrochemistry. Electrochemistry is concerned with oxidative and reductive reactions, reactions involving the motion of electrons between various compounds. Electrons are involved with all forms of chemical bonds. In some types of chemical reactions, electrons are donated by some compounds and accepted by others. When the motion of electrons can be harnessed, such as by batteries, the reactions and processes are part of the study of electrochemistry. So here's an interesting thing that you'll probably learn in chemistry. I'm sure you will. It's called redox reactions. So here's the simplified version. Whenever anything gains electrons, we call it reduced. And whenever anything loses electrons, it's called oxidized. So you see here, agent A lost 2 electrons right here. So here it's lost these 2 electrons, so it's been oxidized. These 2 electrons have been transferred to agent B, and now agent B had gained 2 electrons, and that's called reduction. So oxidation and reduction. You could think about it as Leo the lion goes grr, or oil rig. This is a great mnemonic. Well, you could use either of them. So Leo the lion goes grr. So losing electrons, oxidation, gaining electrons, reduction. Or oxidation is losing electrons, reduction is gaining electrons. And that really helped me out. And here's another example, and it shows how electricity works. Now, electricity is when electrons flow, and that's what creates electricity. So the flow of electrons is electricity. And when electrons flow in a wire, you could put something like a light bulb here and it will light up. And as long as there's electrons flowing, the light bulb will be lit up. But you can see that zinc is losing electrons. The electrons are coming from zinc to copper. So my question to you is zinc being oxidized or reduced? Well, it's losing electrons, so it's being oxidized. Copper is gaining electrons, so it's being reduced. Some applications of electrochemistry are obvious, such as the chemical processes that occur in batteries, both solid and liquid. D-cell or AA cell batteries are solid batteries, and car batteries are liquid batteries. Other types of electrochemistry are less well known. Electroplating of various items is the process of coating an item with various metals or other compounds by electrochemical processes. Other aspects of electrochemistry have more unfamiliar but important applications. Electrolysis of water produces hydrogen and oxygen gas, both of which are used in many ways, including rocket fuel for space exploration. Okay, now colloid chemistry. Colloid chemistry is used to make and understand the behavior of various substances in suspension in a solid, liquid, or gaseous media, as opposed to things dissolved in those media. Examples of colloids would be things like blood and smoke. Blood is basically a water solution in which many solid and gaseous substances are suspended, but not dissolved. Dissolved basically means things are broken up into its formula units, for example, like NaCl, and then NaCl is further dissolved into Na plus ions and Cl minus ions. But in a colloid, the molecules are more suspended and they aren't necessarily dissolved or broken apart. Smoke and clouds are colloids in that the media is air, but the substances suspended are either dust and other solids or water droplets. That's how clouds form. And you probably learned about the hydrologic cycle, also known as the water cycle, when the water molecules evaporate and get higher and higher into the atmosphere, it needs to have things to condense onto. And once gaseous water molecules condense, they form clouds. But again, they need to have something to be condensed onto, and that's the dust that's suspended in the air. Inside all living cells, many things are dissolved, but many things are suspended and not dissolved. Therefore, the cell is a collection of colloidal substances. To picture a colloid, imagine a snow globe. This is a paperweight consisting of a plastic or glass globe in which white flakes of material are enclosed. When you shake it, the flakes are temporarily suspended in the solution. While they eventually fall to the bottom, before they do, you have a temporary colloid. True colloids do not settle out, but stay suspended for very long periods of time. The difference between the snow globe and a true colloid is mostly the size of the particles that are suspended. True colloidal particles are much smaller. Okay, photochemistry. Photochemistry is the study of chemical reactions and radiant energy. This includes both the absorption and emission of radiant energy during or as the result of chemical reactions. So photo means light, like in photosynthesis or photography, for example. And light is a form of energy, and the energy of the sun radiates about 93 million miles away on average to warm up the earth, and is part of what helps sustain life here on earth. Photographic film is one of the most common technologies to result from this form of chemical study. Just to say, you see this word technology here? Well, it's technologies, but still, it's usually coupled with science, so science and technology. Science, the word, basically means knowledge, and technology means the proper application of such knowledge, the proper application of science. That is what technology means. It's not all electrical. You might hear technology and think, electronics, gadgets, game consoles and virtual realities and all that, but that's just one form of technology. If you're interested, I already have the photography merit made here on YouTube. It's a green merit that I'm not sure if you've taken, but we go over film, light, the lens assembly, and how things were back in the day of SLR cameras. And also basic, brownie boxes, the idea of the snapshot, and eventually the disposable film cameras that some of us, like me, grew up with before 99% of everything went digital. But this was an application of using light, and it was George Eastman who founded Kodak in the late 1800s that began selling film. And so the film is exposed to the light, hitting it, and captures the image. Photolithography, or printing with light, is also a form of photochemistry. Generally, photochemistry is concerned with chemical changes that are triggered by the absorption of light energy. The most common type of this absorption is the ejection of an electron by the chemical absorbing the light. That electron, in turn, can bring about chemical changes. Okay, thermodynamics. Thermodynamics is a branch of physical chemistry concerned with the energetics of chemical reactions. During chemical reactions, energy is either released or absorbed. Also, during chemical reactions, entropy, or the randomness of a system, is either increased or decreased. So here's an example of two different basic reactions in thermodynamics. You have the exergonic reaction, which means that energy is released or energy exits from the reaction. You could think about it that way. The delta G means the Gibbs free energy, and it being less than 0 means that it's a negative number. Basically, the rule of thumb is if you see a delta G value being a negative number, then that means the reaction is spontaneous. That means it just happens naturally. You don't have to put in energy in order for the reaction to go. For example, if you take an ice cube and put it out to room temperature, it's going to spontaneously melt. If you put a ball up here on a mountain, for example, it's just going to roll down, but it's going to take energy to freeze water. It's going to take energy to push the ball back up right here, and those are just a couple of examples of spontaneity. Endergonic reaction is where the reaction needs to absorb the energy. It's not spontaneous. It's thermodynamically unfavorable when that happens. So, for example, you have the reactants right here. You need to invest a little bit of energy, and then energy is released to form the products. And the energy of the products is down here, which is less than the energy up here, so that makes it more favorable. Think about holding a big 100-pound stack of books in one hand, and you just hold it there. Well, pretty soon it's going to be unbearable to hold as you lose energy. Your arm may start to lower, and if you don't put it down right away, it might all collapse and fall to the ground. It's kind of a bit like that with nature. Nature wants to be in the lowest energy state as possible. Otherwise, it's like nature holding a big stack of heavy physics textbooks, for example. Okay, here's another illustration that I have illustrating entropy. Now, what's entropy? You could think about it as the amount of disorder. It's more than that, but basically, in basic sense, entropy is basically how random or not so random something is. A solid, for example, has the least amount of randomness. Everything is ordered and together. And then as entropy increases, or the amount of disorder or randomness increases, then it loses some of that order and it begins to fall apart. And then if you increase it more, then it really falls apart and starts flying around in all different directions very rapidly. And that's when you have a gas, for example. So think about it like your room. Once you get your room all cleaned and then give it some time, what's going to happen? It's going to be messy all over again. That's kind of it, going from low entropy or an ordered room to less entropy, and everything's randomly dispersed all across your room. And so this gets into the second law of thermodynamics. The third law of thermodynamics, I believe, says that the entropy of a perfect crystalline structure at 0 Kelvin is 0. And then the 0th law of thermodynamics, long explanation short, is that when two or more objects come in contact with each other, the heat is going to distribute all throughout until there's thermal equilibrium. In other words, the hotter object's going to get cooler, the colder object's going to get warmer, and pretty soon there's going to be an equilibrium. And then the first law deals with internal energy, and it fundamentally states that energy is neither created nor destroyed. Kind of a bit like the law of the conservation of mass, that matter is neither created nor destroyed, which is another law that you'll find in chemistry. The net change in both potential energy, which is the enthalpy, and the randomness, which is the entropy, of any given reaction is expressed as a change in the free energy of the system. Changes in this free energy can be measured and predicted. This information can then be used to predict the likelihood of a chemical reaction, its direction or equilibrium, towards products or starting materials, also known as reactants, and how complete the reaction will be when it stops. The statistical nature of this discipline is due to the inability of chemists to predict the behavior of individual atoms and molecules. This is a consequence of quantum chemistry. However, chemists can predict the probable behavior of large numbers of atoms and molecules, which, if the population is large enough, generally follow the observed rules of thermodynamics. So basically, to put everything into a mathematical equation and mathematical values is not going to be 100% accurate, and that's pretty much why you need statistics and such. But it's nearly spot on. It's like close enough and such. But in nature, it may not line up with the numbers and the theoretical values that you have calculated. And this is called error, and then you could do calculations with error, but that's something that I'm sure that you'll learn and calculate if and when you take chemistry classes. So here's the Gibbs free energy equation. This says that the Gibbs free energy, or the change in it, equals the change in the enthalpy minus the temperature times the change in entropy. So that triangle right there is actually delta. It's a Greek letter, and it denotes change. So remember, when it's above an arrow, it denotes heat is added, but in this case it denotes a change. And again, when delta G is negative, then it's a spontaneous reaction, and when it's positive, it's a non-spontaneous reaction. Furthermore, this delta H equals delta U, which is the change in internal energy, plus the pressure times the change in the volume. The internal energy is the total energy inside a system, and this P delta V comes from the ideal gas equation, and this could further be substituted into delta nRT, but just you don't have to worry about that. Okay, let's move on to E, which is chemical kinetics. Chemical kinetics is basically statistical mathematics applied to measuring and predicting the rate of chemical reactions, basically how fast or how slow are chemical reactions. While thermodynamic chemistry can predict the course of a chemical reaction and its consequences, it does not address the issue of how fast the reaction will proceed. Most often, chemical reactions proceed in a series of steps. Chemical kinetics can be used to determine the rate of each step. Since the overall chemical process is limited by its slowest step, speeding up a chemical reaction requires identifying that slow step so that it can be optimized or used, basically. And then you'll learn about the differential rate laws, the integrated rate laws, half-life expressions, and such. And what physical chemists often like to do is convert a lot of things into linear equations. Chemical kinetics can be used to understand the mechanisms of each step in a reaction to allow chemists to fine-tune each step to achieve the desired rates of reactions. Often, chemists will identify and use chemical accelerators called catalysts. These catalysts can be used to speed up a particular step in a chemical reaction, without itself undergoing any change, as I said earlier. Often the effect of a chemical catalyst is such that with one, a chemical reaction can occur that otherwise would be so slow as to not occur at all, in spite of all the facts that the thermodynamics of the reaction would indicate otherwise. In living cells, catalysts are used for almost all chemical reactions. These catalysts are specialized proteins called enzymes. And here is an illustration of what enzymes do. So this right here is an enzyme. It's a protein. And then you have a substrate, any molecule that can fit inside the active site of an enzyme. And then a chemical reaction occurs to break the substrate apart into two or more pieces. And then enzymes are also used to build small pieces of molecules into one big molecule. That's known as anabolism. This right here is known as catabolism. But anyway, you notice that the substrate and the active site have to fit together like a lock and key, so it's called the lock and key method. And it's kind of a bit like glucose and insulin. Insulin has to fit inside certain receptors in order to open the cell enough to let the glucose in, but there's that lock and key mechanism there too. But again, a substrate is something that has a specific shape to attach to the active site of an enzyme, and then we have an enzyme substrate complex, and then it breaks apart, the substrate does, into two different molecules, smaller molecules, to form an enzyme product complex, and then you just have products leaving the enzyme, and now it's ready for another substrate to come in. Usually, a lot of enzymes require cofactors. What are they? Those are your vitamins and minerals. That's why everybody says how important it is to have your vitamins and minerals, to consume vitamins and minerals as you grow up and as you live your life. Always make sure that you have vitamins and minerals because they act as cofactors. And what do they do for the enzyme? It turns the enzyme on. So you could have an enzyme and a substrate that bind to each other, but it's not going to have a chemical reaction because there isn't a cofactor. A cofactor usually is inside the active site before the substrate attaches. And again, it sort of turns on the enzyme. Without the cofactor, the enzyme is called an apple enzyme, and with the cofactor, it's called a hollow enzyme. And that means the enzyme is activated with once you have the cofactor on. Vitamins and minerals, real quickly, what's the difference? Vitamins are organic material, and synthesized by living organisms. We could synthesize vitamin D when we're out in the sun. Let's see, oranges could synthesize vitamin C. Well, minerals, on the other hand, are inorganic material, and those are like your metals, your potassium from bananas, your calcium from milk, zinc, magnesium, manganese, and such, iron. Remember what iron's good for. It's good for our blood, the hemoglobin. It's good to pick up the oxygen when the blood circulates in our lungs, specifically the alveoli in our lungs, lest you get iron deficiency anemia. And anemia is just a blood condition, and iron deficiency anemia is when the body is deficient of iron. Iodine is another good mineral because that could help prevent goiter. And there's quite a few applications for each mineral, so you could look those up if you're interested in that. But that's kind of why vitamins and minerals are important, because they act as cofactors. Another quick thing is that a cofactor that's a vitamin or an organic material, organic substance, is known as a coenzyme. So another word for a cofactor, when it's a vitamin or something organic, then it's also called a coenzyme. So let's look at this graphic here on the left. You see the reactant right here, and this on the y-axis is the total energy. You see that it's thermodynamically favorable for this process to occur because the energy of the product is lower than that of the reactants. However, you need activation energy, which is the energy needed for a reaction to occur, to get to convert the reactant into products. You see that you have a high activation energy, meaning that you need a lot of energy that something may or may not have. But if you have an enzyme, that's going to lower the activation energy so that you'll get more products that way, and it's more thermodynamically favorable. Okay, requirement 9. Define DNA and describe where it is found. DNA, or deoxyribonucleic acid, is the information storage molecule of all living things and is found in all living cells. In cells that have a nucleus, known as eukaryotes, DNA is found in the nucleus. The information stored by DNA is called the DNA code. This code is used by living cells to make the components of the organism and to mediate all of the chemical behavior of those components. Even complex actions and behaviors of many animals are the result of information stored in DNA. So this molecule right here is the reason why you are you. It's the reason why you're a certain height, you have a certain hair color, your hair is the way it is, meaning either wavy or straight or curly. It's the reason of what makes you yourself. It's also the reason why some people might have some disabilities, or they might have things that other people don't have and such. It's because of our DNA. So here's a picture of an animal cell. This right here is the nucleus, so let's zoom in on the nucleus. And inside the nucleus, you have this material right here. Well, the material right here is the chromosome. And if you take, or when you take biology, if you haven't already, you'll learn more details about chromosome, chromatid, chromatins, all that. But basically, you have the chromosome, and it's usually an X. Well, it's not really an X until they're ready to divide, which is known as mitosis, but never mind about that right now. But inside the chromosome is DNA. Well, I mean, that's what chromosome is made out of, DNA, as well as proteins as well, which we'll get to right now. Let's look further into the chromosome. It's made of all of these supercoils that you see here. So you have all of these supercoils, and if you look closely, they are wrapped in coils. So you have coils, and then the coils are wrapped in a supercoil. But if you look closely, you have all of these clumps called nucleosomes wrapped with this thread, as you notice. Well, each clump is made of histones, proteins, which are the individual spheres as you see here. But what's this thread wrapped around? The thread is DNA. So that's just a little closer look. As a molecule, DNA is a long chain of building blocks known as bases. These bases are like the letters of an alphabet. However, there's only 4 letters in the DNA alphabet, and in spite of the low number of letters, there are more than 3 billion of them in a single human cell. Normally, 2 chains of DNA bind together to form a helix, which is shaped like a twisted ladder. So imagine that you have a ladder. Each rung is a base pair, and then it's twisted. So let's look at DNA right here. You have the twisted ladder, and you have the rungs. Well, there are 2 bases per rung, known as a base pair. You have 4 different bases in DNA. You have cytosine, guanine, adenine, and thymine. And in RNA, you have these 4, cytosine, guanine, adenine, and uracil. So C, G, and A are the same. The only difference is that you see uracil in RNA and thymine in DNA. And when I was taking biochemistry, I learned that there's more than just these 5. You also notice that between uracil and thymine, the only difference is a methyl group. Thymine has an extra methyl right here. A methyl is CH3. And so therefore thymine is also known as 5-methyl-uracil. But anyway, that's actually one difference between RNA and DNA. RNA is typically single-stranded, and DNA is double-stranded. If you see U anywhere, then number 1, you won't see T, and you know that you have RNA. If you see T, then you know that you have DNA. Here's some more detail about the nucleotides. Remember, biology typically looks at shapes and the big picture, and biochemists typically look at the individual atoms and keeping track of the atoms, counting the atoms and all that. But this is basically a few of these up close. So I'll explain this, and then I'll explain just a little bit more about the difference between the sugars of DNA and RNA. But anyway, here is the base. You have T right here because, or thymine because of the T here, and that's bonded to the sugar, and the sugar is bonded to the phosphate. Okay, that in itself is one nucleotide. Okay, if it didn't have the phosphate in it, then it would be called a nucleoside, and that's when you learn about ATP, DATP, GTP, and all that. But besides that, that's one nucleotide, and then that nucleotide is bonded to other nucleotides down the ladder, so to speak. So you have a phosphate sugar, phosphate sugar, phosphate sugar backbone. You also notice the shapes of guanine and adenine. They're a 2-ring structure. Another thing that you'll notice is that according to Chargaff's rules, not to thoroughly explain it, but according to Chargaff's rules, cytosine always bonds with guanine, adenine always bonds with thymine, and if it's RNA, adenine will bind to uracil. You will also notice that it's a 2-ring structure that's bonded to a single-ring structure each time, and you'll notice that cytosine is blue, guanine is green. Well, it really doesn't have the colors, but for illustration purposes, you'll see that blue and green always bond together in this diagram. Same thing with A and T. Also, single-ring structures like thymine and cytosine are called pyrimidines, and guanine and adenine, the one with the 2-ring structure, are known as purines. I might as well say this now so it may be easier for the next thing I want to show you, but you have the base, you have the sugar, and you have all these numbers here. Well, we keep track of individual atoms, and every time that you see a point like this, that's a carbon right here. So when you see 1', 2', 3', 4', those are carbons, even though we don't write the C's for this. And that's sort of used to save time. When you take organic chemistry, you'll learn about line angle structures. But anyway, we say 1', 2', and so on because we already use 1, 2, 3 first for the base, and to avoid confusion, instead of using 1, 2, 3 again, we'll just do 1', 2', 3', 4', 5', and all that. The 1' carbon is what's bonded to the nitrogenous base right here, and it's called the glycosidic bond. It's called a nitrogenous base as well because it contains nitrogen, as you see, but this right here is called a glycosidic bond. The 3' carbon is what's bonded to the phosphate group of the nucleotide below, and then the 5' carbon up here is what's bonded to its phosphate group, and then that's going to be bonded to the 3' carbon of the nucleotide above. And these are known as phosphodiester bonds over here, as you could see right here. Alright, now there's one more difference between DNA and RNA that I want to share with you, and it's this. The difference between DNA and RNA, besides thymine and uracil, is its sugar. So the first thing I want to ask you is, what is the difference between these two Haworth projections? So Haworth projection is just a way to visualize certain molecules, like you have Fisher projection and so on and so forth. But what's the difference right here? Take a moment to find out. Alright, here's the difference. You see that this one at the 2' carbon is bonded to an OH, and this one is just bonded to an H. Now I'm going to tell you that one of these is deoxyribose and the other is ribose. Which one do you think it is? Okay, here's the answer. Notice that this one has oxygen to it and this one doesn't. Let's make believe that we just grabbed this oxygen and pulled it out. Okay, think about that as deoxifying this sugar right here, as if it's deoxified to this sugar. Therefore, this is ribose and this is deoxyribose. Deoxy. Okay, just look at that and think about it as if an oxygen had been removed, which it has, and it's specific to the 2' carbon. So DNA contains deoxyribose and RNA contains ribose. Okay, requirement 10. Obtain a copy of the periodic table of the elements and complete the following. So here is the periodic table. A. What purpose does the periodic table serve? It's the chemist's directory to the elements. And I kid you not, but all throughout my chemistry classes, I really refer to this a lot. And I'm sure that you will too. You could get a lot of information. You could get information based on where the elements are on the periodic table. You could get information by the atomic weight, as we'll talk about later. And that's what I really used the periodic table for, was to find the atomic weight of the elements. That way I could calculate things like the molar mass, for example. And pretty soon after using some of the common elements like hydrogen, carbon, nitrogen, oxygen, chlorine, sodium, after you use them so many times for months and years, you kind of have the atomic weight memorized. And this periodic table kind of rounds a lot of the atomic weights. For example, hydrogen is really 1.00794, carbon is 12.0107, nitrogen is 14.0067, there's a 4 at the end of oxygen if you go one more digit. So a lot of periodic tables kind of round. But what I like about this periodic table, it kind of shows how many electrons are in each shell, and we'll talk about shells later. So for example, chlorine has 3 shells occupied with electrons. The first one has 2, which is its max. The second one has 8, which is its max, and the third one has 7. And argon, you just add an extra proton and an extra electron, and so you have 8 electrons in the third shell. But we'll talk more about electrons later. But basically, this is kind of what it served, especially for me. That's mainly what I used it for, was for the atomic weight. Its very strong patterns of chemical behavior appear to fit with elements in the vertical columns. The periodic table fits a very well special pattern, which is dependent upon the valence number. Valences are concerned with the number of electrons in the outermost shell around the various atomic nuclei. One more thing about the name of the periodic table is, why is it called the periodic table? Well, remember back how the periodic table was developed, and people like Dobereiner, for example, or Mendeleyev, they ordered the elements based on the atomic weight. However, Moseley came along and ordered the elements based on atomic number. But when you do that, you see that certain properties of elements recur periodically. That's why it's called a periodic table. So for example, everything in this column right here, column 1, will have similar properties, and everything right here in column 7 or 17, depending on the periodic table, this could be 7a or 17, they have its similar properties. The noble gases are inert. That's one of the similar properties it has. Another similar property is that it has a full octet, with exception to helium, in its valence shell, which is the reason why they're inert. And that's kind of how Mendeleyev was able to predict elements that haven't been discovered yet. But just to say, when you list the elements based on atomic number, like 1, 2, 3, 4, and all that, then it's kind of a bit more helpful than listing them based on atomic weight, because some atomic weights don't go in order. Like for example, cobalt atomic weight is 58.93, but nickel is 58.69. However, cobalt has 27 protons and nickel has 28, and the number of protons is the atomic number, so when you order based on atomic number, it's basically more easy to work with in such a table. So simply put, that's why it's called the periodic table, because when ordering elements, certain properties recur periodically. Okay, so to talk about valence electrons, here's chlorine. Chlorine has 3 shells, as you see right here. So you have shell 1, shell 2, and shell 3. Or I should say this, chlorine has 3 shells that are occupied. I'll put it that way. But chlorine's outermost shell is called the valence shell. Any element's outermost shell that's filled with at least 1 electron is called the valence shell. And the electrons inside the valence shell is called the valence electron. So chlorine has 7 valence electrons. How many does neon have? If you said 8, that's correct. The outermost shell, the second one, has 8 electrons. And this is very important because this is an octet. And according to the octet rule, think about this. Every element of the periodic table spends its entire life trying to achieve the octet, or at least just think about it that way. It's trying to achieve an octet, and it will donate, it will share electrons in order to do that, except for like helium and hydrogen. I mean, I'm sure they'd be satisfied with 2, and maybe lithium and beryllium, if they just get rid of their electrons, then they'd have a duet, and that's called the duet rule. But basically, that's what makes it stable. Okay, so now I have a quick quiz. How many valence electrons does lithium have? 1. How many does fluorine have? 7. How many does aluminum have? 3. So, the periodic table is very useful in predicting many attributes of the various elements. Acid-forming elements are found at the right-hand side, while base-forming elements are on the left. Bases typically have OH attached to it, and an OH group is called hydroxide, just like a CH3 group is called a methyl. You have lithium hydroxide, sodium hydroxide, magnesium hydroxide, potassium hydroxide, and such, and those are bases. And just like it says up here, base-forming elements are on the left, right here. And acid-forming elements are typically found in the right-hand side. Hydrogen usually denotes an acid, and hydrogen is over here, but technically hydrogen doesn't really belong here in the periodic table, because it's not like the other alkali metals. Sometimes scientists put hydrogen off to the side over here. But anyway, if hydrogen is bonded to chlorine, for example, then that's like hydrochloric acid. But you also have sulfuric acid, nitric acid. You also have hydrobromic acid, hydroiodic acid, and others as well. So the elements in the first and 7th rows are very reactive, while the ones in the middle are less so generally. Also, I have a picture here, or a graphic here, illustrating the periodic trends, as it's called, like electron affinity, ionization energy, atomic radius. Typically, elements right over here are metals, and elements over here are nonmetals, meaning gases. A couple of elements are liquid at room temperature, and then you have metalloids. Some of the defining characteristic or properties of metals is that they're shiny, they're malleable, which means they could be hammered into a sheet, they're ductile, which means that they could be drawn into wires or a wire. They're typically good conductors of heat and electricity. But metalloids, they're neither liquid nor gas when in room temperature, but unlike metals, they're poor conductors of heat and electricity. If you try to hammer them, they'll just break apart like little pieces of rock because them being brittle, you can't draw them into a wire and such. Other characteristics are atomic radius. Now first, columns are known as groups or families, and rows are known as periods, like period 1, 2, 3, 4, 5, 6, and so on. But as you go from one period to the next, think about it like adding an extra occupied shell. And when you do so, the radius of the atom will be bigger, and such as you get more and more shells occupied. However, through other things like z-effective, the further left you go to the periodic table, the bigger the atomic radii is. It's because when you add more protons and electrons, the more effective nuclear charge there is, the closer the electrons are going to be pulled toward the nucleus, and hence the smaller the radius is. So you also have electronegativity, which is the kind of the desire of an element to attract electrons toward itself, and that increases, like non-metallic character, that sort of increases, like fluorine right here is the most electronegative element. Francium down here is one of the least electronegative elements. Ionization energy is basically the energy needed to ionize, and what ionize means is, in this case, is to get rid of an electron. Things like group 1 elements, the alkali metals, such as lithium, sodium, potassium, rubidium, cesium, and francium here, they all have one valence electron. And if it gets rid of that valence electron, then that also gets rid of the valence shell. The valence shell is now the one that was underneath it, and that is occupied by 8 electrons, satisfying the octet rule. And so these atoms would be glad to get rid of that valence electrons, and since it would be glad to, so that it could be stable with an octet, then it doesn't take a lot of energy to do so. Try to get rid of 2 electrons to achieve an octet. That's going to take a bit more energy, and it's going to take more energy further still when you go to the group 3A or the group 13 elements. And then imagine the halogens right here. They have 7 valence electrons, and because of that, it needs one more electron to achieve an octet. So it wants to gain that one electron so bad, that's why it's highly electronegative, versus trying to get rid of 7 electrons, which is going to take an enormous amount of energy, and with that said, it's thermodynamically unfavorable for that. I mean, anything that typically takes energy is thermodynamically unfavorable. Things that releases heat and energy is typically favorable. So here's sort of an example of what I was just saying earlier. Sodium here has 1 valence electron. Chlorine has 7. So chlorine is 1 electron away from a full octet. Well, sodium has that 1 electron. Sodium, it doesn't take a lot of energy for it to get rid of that electron. So what it's going to do is that sodium is going to bond with chlorine. And since it's so favorable, it's known as an ionic bond. The chlorine is going to pull that electron away. Sodium is gladly going to give its electron away, but that's going to create a bond between the two. Therefore, you have sodium chloride, which is table salt. What's also interesting is that on its own, chlorine is a deadly gas, sodium is very explosive in water, but put the two together and that's basically table salt. Okay, B. what is the total number of discovered elements? And then of those elements, how many are natural and how many are synthetic or man-made? There are 118 total elements known right now, from hydrogen to oganesson. 92 of them are natural, from hydrogen to uranium, and therefore currently 26 of them are synthetic or man-made. They were synthesized in the lab. These are typically radioactive and highly unstable, and if I heard correctly, some of these only last for seconds and maybe even fractions of a second, but they synthesized them for however long, so it was added to the periodic table. What's neat is finding a book from the 90s or early 2000s and seeing all the outdated periodic tables. But that's also history right there. It's like this is what chemists used back in the day. Okay, C. What is meant by the, quote, atomic weight value, and how is it used to characterize elements in the table? Now first, I might as well get this out of the way right now, the difference between weight and mass. Weight is the measurement of the gravitational pull that an object has, and it's dependent on where you are. It depends on where you are on Earth, and it also depends on what celestial body you're on. If you're on Earth, if you're on a satellite like the moon, or if you're on another planet. Mass is how much matter is in something. Your mass is going to be constant, unless your arm gets cut off on the way to Mars or someplace. But other than that, your mass is going to remain constant. All the matter that's in you, all the organs, the organ systems, the blood, lymph, everything that's in you is going to stay constant. So your mass is going to stay constant. The weight is going to change because of the gravitational pull. That's why places like Mars, you could jump 3 times higher. The moon's gravity, well, let's say this, Earth's gravity is 6 times more than the moon. That's why on the moon, you could jump higher there too, and such. The gravity on Mercury and Mars is 38% that of Earth. Venus is 91%. So let's say that you weigh 100 pounds on Earth. If you were to go to Venus, for example, you would weigh 91 pounds. If you weigh 200 pounds on Earth and you go to Mars, you would weigh only 76 pounds on Mars, which is 38 times 2. And if you weigh 100 pounds on Earth, then you'd weigh 38 pounds on either Mercury or Mars. So weight is going to fluctuate, mass will not, and when you weigh things out in a balance, it's calibrated and will adjust accordingly to give you the mass. So it's pretty interesting, but usually when people say weight, they might be meaning of mass. And in physics, you'll learn that weight equals the mass of an object times gravity, and that's what balances are calibrated to, and they will adjust to give you the mass. But gravity, you have to multiply by a magnitude of 9.81 meters per second squared. But I will say this real quickly, back to physics. My physics professor, one of them, said that technically physics and chemistry are the same exact thing, just 2 different ways of looking at it. And of course you need to have some chemistry knowledge anyway in physics, but just quoting what he said. So, well, anyway, that's physics, but back to chemistry. Anyway, here is a carbon atom. You see that you have the number 12 here and the number 6. Well, this is one way to write each element. You have the element symbol. C is carbon, just like Cl would be chlorine and N would be nitrogen. The top number is actually the atomic mass, and the bottom number is the atomic number. And typically this is also known as Z, and this is known as A. So basically the atomic number is the number of protons there are in an element, and that will never change. If it were to somehow add a proton and make this 7, then it's no longer carbon, it would be nitrogen. If it were to take away 2 protons and make this 4, it would no longer be carbon, it would be beryllium, for example. So the number of protons there are determines what element you have. The sum of the protons and the electrons are its atomic mass, which is 12. So 6 plus 6 is 12. If you look here, there are 6 protons and 6 electrons. The number of neutrons don't factor in to the atomic mass. It does for the atomic weight value, but we'll talk about that later on. But the number of neutrons can fluctuate. The protons are positively charged, the electrons are negatively charged. So when you have an equal number of protons and an equal number of electrons, they totally counterbalance each other out to have a overall neutral element. If it were to have more electrons or less electrons, then it would be called an ion. If you have a positively charged ion, it's called a cation. If you have a negatively charged ion, it's called an anion. And one proton is 1,836 times the mass of an electron. But even though an electron is far more smaller than a proton, their charges are such that they counterbalance each other out and make it electrically neutral. And just to say a neutron is just a little bit bigger than a proton, a neutron is 1,839 times the mass of an electron. But let's take a look at what the periodic table says. You have C, which means it's carbon. The atomic number is 6. That's right, that's the number of protons. But what's this number right here, 12.0107? This isn't 6 plus 6. Well, this right here is the atomic weight. This is the atomic mass. But let me explain how we get to this figure. Carbon appears in 3 isotopes. An isotope is where you have a different number of neutrons. So carbon-12 has 6 protons, along with carbon-13 or carbon-14. It has to, otherwise it's not carbon. And to be electrically neutral, it would have to have 6 electrons. If it doesn't have an equal number of electrons compared to protons, then it's an ion. But if it has different numbers of neutrons, then it's an isotope. Taking carbon-13, for example, it has 6 protons, but in this case 7 neutrons. So since it has 6 protons, it's carbon, but it doesn't have 6 neutrons, it has 1 more. And then carbon has 1 more than that, 8 neutrons. But what about these percentages? This is the percentage of how abundant this isotope is in nature. So let's say in theory that you have 1,000 carbon atoms. 989 of them would be carbon-12, 110 of them would be carbon-13, and about 10 would be carbon-14. That's how they're found in nature, and these are the average percentages right here. Therefore, the atomic weight is the weighted average of all the isotopes known. And you use a device like a mass spectrometer to find out percent abundance and such. So it's basically the mass of the isotope times the abundance, or the percent abundance, or the fractional abundance. And then you add that to the other two while taking the average. So normal average would be just like adding the masses of each and then divide by 3. Well, you have to take into account that there's a higher probability of picking out a carbon-12 atom in a bag of carbon atoms, theoretically, let's say, than a carbon-13 or 14. So it takes a percentage of the amount, and that's why it's called the weighted average, not just a plain average. So here's a graphic to help illustrate the two. Atomic mass is the sum of the protons and neutrons of a single atom. So in this case, the atomic mass of carbon-12 is 12, the atomic mass of carbon-13 is 13, and for carbon-14 it's 14. But the atomic weight is the weighted average of the atomic mass of all natural isotopes of an element. And that's where all these decimal numbers come from. And a lot of periodic tables, it depends. A lot of them just round off. You might see 12.01, for example. Oxygen, you might just see 16. But it depends on who made that particular periodic table for your textbook or reference sheet. Atomic numbers also characterize elements. An element is defined as a substance made of atoms that have the same atomic number, like what I was saying before. The atomic number is the number of protons in a given atom. The number of protons determines the number of electrons that the atom can possess in a neutral state. The number of electrons in the outermost orbits around the nucleus determines in a very large degree the chemical nature of the element. For this reason, the atomic number of an element is used to place it in the periodic table. Atomic weights are based on carbon-12, the standard chosen in 1961 by the Commission of Atomic Weights. So a group of scientists agreed that the weight of a carbon-12 atom would be 12U, or 12 AMU, which stands for atomic mass units. And that was set as a standard. So every other element known and all the isotopes are measured based on the carbon-12 atom. So going back real quick to carbon-12, the mass of the carbon-12 isotope, it would be 12.0000, for instance. And then you multiply that by 0.989, and then you add it to the mass of carbon-13, multiplied by 0.011, and so on for carbon-12, to get 12.0107. So essentially, chemistry is really math-oriented. Okay, D. What is the shell of an atom, and how does the shell determine the families and groups of elements that appear in the table? How does the function of the shell help us to understand the atom's behavior? The term shell is used because the electrons in atoms are arranged in orbits corresponding to various energy levels or shells around the nuclei. Each shell can accommodate only a certain finite number of electrons. As each shell is filled as one goes up the periodic table, the next electrons are positioned in the next outer empty shell. Atoms have a strong desire to fulfill the octet rule, with exception to hydrogen and helium, in which they would prefer the duet rule. So let me help elucidate all that. So here's hydrogen, and you have all of these shells around hydrogen. These shells are also known as energy levels. So a hydrogen has one electron right up here. Well, all these shells exist, but they're not always occupied and such with electrons. So in order for electrons to move up an energy level, energy must be absorbed. That energy could come from, let's say, a photon of light. Light could come in, and then that electron absorbs the energy and it excites it to another energy level. Well, when that energy is released, and it has to be a specific value, then that electron will go down and it will emit that photon of light. Light in the visible spectrum, for example, ranges from like 400 to 700 nanometers and such. That's red, orange, yellow, green, blue, indigo, violet. And they have a specific amount of energy. Well, let's say, for example, you have a wavelength of light of a specific color, and then hydrogen absorbs it. Well, when it releases energy, it releases that wavelength of light, and you see that color. But you'll probably learn that when you learn more thoroughly about the electromagnetic spectrum. And then here are orbitals. So a shell are different energy levels, but each shell could have more than one orbital. The first shell, so like n equals 1, or 1n, according to this diagram, has only a 1s orbital. It only has one orbital. But the 2n, for example, has the s and the p's, and there's 3 different p orbitals, depending on the axis and such. And each orbital could hold up to 2 electrons each. And there's all these laws and quantum numbers that you'll probably learn, like the Aufbau principle, the Pauli exclusion principle, Hund's rule, and such that you'll learn later on. But basically the definition of an orbital is really a mathematical equation used to predict where you could locate an electron like 95% of the time. Well, you know, electrons are whizzing around the nucleus in these orbitals or these regions, so you can't always be certain where an electron is, and that's kind of one of the major parts of the Heisenberg uncertainty principle, which states that you could pinpoint where an electron is, but you can't know the momentum, or you could find the momentum, but when you do, you won't know exactly where it's at. And then you have these d orbitals and these f orbitals, and the f orbitals are kind of a bit like the bigger elements, especially the lanthanides, the actinides, and such. But this really gets into quantum mechanics. But one thing is that each orbital could contain a maximum of 2 electrons. So what I said right here is that the n equals 1 shell is basically the 1s orbital here. So it could hold only up to 2 electrons, and that's what the first shell can hold. The second shell can hold up to 8 electrons. Well, the second shell has a 2s orbital, which is bigger than the 1s, along with the 3 p orbitals. Now electrons are not always in these orbitals, but elements like the noble gases have all of them filled. So taking neon, for example, you have the 1s orbital that has 2 electrons. You have the 2s orbital around that, that's in the n equals 2 shell. So that's another 2 electrons, so you have 4 now. And then you have 3 p orbitals, so that's 2 times 3 is 6. 6 plus 4 is 10, and therefore neon has 10 electrons. But if that didn't really make sense, then just don't worry about that, because I'm sure that you'll learn it later on. So valence electrons and group numbers, real quickly, I just wanted to say on the periodic table, you see all the families, also known as groups, group 1, 2, 3, all the way to 18. Well, some periodic tables have like 1A, 2A, 3A, all the way to 8A, and then the transition metals in between are like 3B, 4B, all the way to 2B. And yeah, you have to look at it to find that it doesn't go 1B to onward. It starts at 3B and then it goes to 2B. But anyway, for the A elements, like non-transition metals, it typically has 1A, 2A, all the way to 8A. You take a look at that column, and that's the number of valence electrons. So like 7A are the halogens. They all have 7 electrons in the valence shell, so they have 7 valence electrons. If it is a periodic table that would show 17, we'll just subtract 10. So group 13 or 3A would have 3 valence electrons, for example. 5A would have 5 valence electrons, or group 15. Chemical reactions occur when atoms approach each other and either swap or share electrons to fill their outer shells. An atom that wants to lose an electron will bind nicely to an atom that wants to gain an electron. An atom that wants to lose 2 electrons will bind either to a single atom that wants to gain 2 electrons or to 2 atoms that each want to gain 1, and so on. This sharing or transfer of electrons form chemical bonds, such as water. Water is H2O, so oxygen wants to lose 2 electrons, so it would bind to either a single atom that would want to gain 2 electrons, or to 2 atoms that each want to gain 1. So hydrogen wants to only gain 1, so that's why you need 2 hydrogens to make a neutral water molecule. One of the donor electrons in oxygen will bind covalently to one of the hydrogens, and the other donor electron will bind to the other hydrogen. When the electrons are actually transferred from one atom to another, the chemical bond is said to be ionic, since the 2 atoms now have more or less electrons than they do protons. They started with equal numbers. Atoms with more or less electrons than protons are called ions and form ionic bonds, and atoms that share electrons form covalent bonds. So like swapping would be an ionic bond, and sharing would be like covalent bonds. And then I added this GIF down here, and it basically shows like when this molecule looks like a hydroxide, an oxygen and a hydrogen, but as it gets closer, it's going to have an influence on this molecule right here. You see that the hydrogens are being pushed away due to repulsion, and then another atom is going to be detached as the red one and the blue one bonds. Okay, requirement 11. Identify the following chemicals and list the atoms in each. So pause if necessary, but this is also a quiz for you. The first one is H2O. So what is this molecule first of all? This is water, also known as dihydrogen monoxide. So what atoms are in water? It contains 1 oxygen and 2 hydrogens. These symbols right here, this is delta, lowercase Greek letter delta. This is delta plus and delta minus. It just denotes partial charges. Oxygen is next to fluorine, so it's really electronegative, not as much as fluorine, but it's still electronegative, which means it's going to pull these electrons closer to itself. Since oxygen has hydrogen's electrons closer to itself, there's an overall partial negative charge because electrons are negatively charged, leaving hydrogen partially positive. And then there's so much property with water as a result. That's why ice floats on top of water. Otherwise, this world would probably be massively different, and that's due to hydrogen bonding and such that you'll learn later on. Okay, the second one is NaHCO3, which is this molecule right here. So first, let's identify it. This is baking soda, also known as sodium bicarbonate. So what atoms are in sodium bicarbonate? It contains 1 sodium, 1 carbon, 3 oxygens, and 1 hydrogen. The next is NaCl. And this is what it looks like. I'll explain here shortly. But what is this? This is table salt, also known as sodium chloride. So salt is an ionic compound. And what are the atoms? 1 sodium and 1 chlorine. So this is basically what ionic compounds such as salt typically look like. It's in this lattice structure. The sodium would be the small purple atoms, and the chlorine would be the green ones. Well, when they're bonded together, it would be called sodium chloride. And then since it's ionic, since this is positive and this is negative, they bond together in an ionic bond. But chlorine, of course, now has an overall negative charge. Sodium has a positive charge. So nearby molecules are going to be attracted. The chlorine is going to be attracted to other sodium atoms, and sodium atoms are going to be attracted to other chlorine atoms and create this crystalline structure. So when you add to water, since water has partial positive and partial negative properties to it, as I was saying before, it's going to pull on the positive and negative parts of sodium chloride and break it apart, therefore dissolving. Okay, D, CO2. What's this molecule? It's carbon dioxide. What atoms does it contain? 1 carbon and 2 oxygens. E, H2SO4. So what's this molecule? This is sulfuric acid. And what atoms are included? It contains 2 hydrogens, 1 sulfur, and 4 oxygens. Since sulfur is in group 3 down here, it could have these 6 bonds. Up here, it would be 4 bonds, and you'll learn about expanded octets for these atoms and beyond, but that would probably be later on in your studies. Okay, KOH. Okay, what's this molecule? It is potassium hydroxide. What atoms are contained in it? 1 potassium, 1 oxygen, and 1 hydrogen. Something I should have said with NaCl is that these are known as formula units. Whenever you have just 1 potassium and 1 hydroxide just by itself, then that's a formula unit. NaCl by itself is a formula unit, and then they all combine together to form lattice structures. Okay, G, H2O2. What's this molecule? It's hydrogen peroxide. What are the atoms? 2 oxygens and 2 hydrogens. Okay, requirement 12. Explain the chemical reaction that the following chemical formula graphically describes. 2H2 plus O2 yields 2H2O. And I use the word yield, and I'll probably elucidate that here in a few moments. Okay, take a pause if you want to. Here it is. It means that 2 molecules of hydrogen gas, and hydrogen gas is H2, it's not H. You have 2 hydrogens bonded together to create hydrogen gas, also known as a diatomic molecule. And 1 molecule of oxygen gas, which is another diatomic molecule, react to yield 2 molecules of water. So again, 2 molecules of hydrogen gas is added to 1 molecule of oxygen to make or yield 2 molecules of water. And you'll probably do 100 of these at least, but it's balancing chemical equations. Under the law of conservation of mass, it says that matter is neither created nor destroyed in chemical reactions. So this is a chemical reaction. You're converting 3 molecules, a total of 3 molecules of gas, into 2 molecules of water total. And you notice that if you add them all up, you have 4 hydrogen atoms and 2 oxygen atoms on both sides of the equation. This is also known as a chemical equation. So you could also just look at this and tell that it's balanced. How many hydrogens do you have? Well, each molecule of H2 has 2 hydrogens, and you have 2 of them. So 2 times 2 is 4. Let's go on this side. For each molecule of water, you have 2 hydrogens and 1 oxygen. Well, you have 2 of them. So 2 times 2 is 4. So both sides balance. Over here, you have 2 atoms of oxygen. And over here, you have 2 times 1. We don't add the subscript 1 because it's implied, which means that you have 2 oxygens. So that balances. Also, this is known as the reactants, and this is known as the product, or the product side. So the reactant side and the product side. Okay, requirement 13 is something that you're going to do at home. So it says, do each of the following experiments. Develop a hypothesis, which basically means an educated guess. It's part of the scientific method. You make hypotheses, and then you design an experiment to test your hypothesis. And in order for something to be a theory, it must abide by the hypothesis, and it also must be reproducible by other scientists as well. Other scientists need to recreate what you've created as well. And that's like an entire crash course on the scientific method. There's a bit more to that, but still, develop a hypothesis or what you think is going to happen prior to each experiment. Then write a report and explain the results of the experiment, including what you learned. This is the first one. You're going to study the reaction of vinegar mixed in baking soda. Here are the items needed and the steps. The second one is to reverse the tarnishing effect of silver. Here are the items needed and the steps. Take a moment to pause or take a screenshot or to copy this down when you're ready. Okay, so big congratulations. You got a wonderful start, a huge start on the chemistry merit. The next step is to show your commander all the notes that you've taken and do some of the at-home things, especially back from requirement 2 and this past requirement 13 and such, and you're almost good to go. And I hope that you do well in any future chemistry classes that you're taking, or if you're taking one right now. Again, I just hope that you do well. Just take your time. Ask questions. That's what your teachers are there for. That's what your professors are there for. Breathe and just don't get too bogged down or panicked. And it's good to take breaks once in a while. I've had those times of frustration the past 5 years and such. And you just have to reassess, reevaluate, ask questions when you need to. Write them down so that you won't forget. And pray for the Lord to lead you, for the Holy Spirit to just give you peace and calmness, the peace that surpasses all understanding, the remembrance while you're taking the test. And I pray that you'll do fine. So once again, good job and keep up the good work.